Okay, exercise 8 to 3. Let's remember that we did not actually fully solve this, and here we are proving the properties of convergent sums, where the sets can be any type of sets. So far we have proved only parts A and B. So today we are going to start with part C. Two more are there, C and D. So let's recall what this thing was about. So it starts with a set X. X is any set, that means X can be finite or infinite, countable, uncountable if it is infinite, any type of set. And two real valued functions are defined on X, f and g. They have X as their domain, such that these two sums are absolutely convergent. This one and this one. They are absolutely convergent. So we have these hypotheses in the beginning of the result, and then after that we have those subdivisions A, B, C and D. A and B we already have seen, we have proved them. So let's now see what we have to do in part C. Part C states this: if the set X is the union of two subsets x1 and x2 which are disjoint, that means they do not have any element in common, then these two sums are also absolutely convergent. Both of them are sums of f values, but now the sets are different, x1 and x2, not the entire x. They are absolutely convergent. So that means they will have values, and their values are linked to the value of this original sum by this formula. So we have to prove this, but this is not entirely what C states. Part C states something more than this, but we are coming to that part which I have not shown here afterwards. Let us first show this much. So that means here also we have two things to show. First we have to show that these sums are absolutely convergent, and then we have to prove this identity. Okay. Since x1 and x2 are subsets of x, of course, and it is given that this series or this sum is absolutely convergent, it follows from the solution to the previous y exercise that this and this, these two sums are absolutely convergent. So you see that we are still using the y exercise. So it's not just something to satisfy our curiosity about these things, but it's actually helpful and in fact essential. We want these things, we want the things that we have seen and we have proved in that y exercise. So in that exercise what we proved and what we are using here is this. So if you have an absolutely convergent series like this and then you consider one like this where the set is a subset of the previous set, then this is also absolutely convergent, and this we proved in the beginning of the solution to this y exercise itself. So that's why we are now directly able to conclude that these two are absolutely convergent. So that means this part is over. R absolutely convergent. So that means now we have three absolutely convergent sums. This one, and this one. And we now want to prove that their values satisfy this equation. But because they are all absolutely convergent, showing this amounts to showing this. X1 and that other sum, it will be over the set X2. Why? That's because absolute convergence of these sums implies by definition that this is the value of this is the value of this, and this is the value of this. In finding out the values, we do not of course consider the 0f values. We discard the 0f values and only consider the non-0f values. So this is what we now have to prove. And this identity already follows from something we have seen previously in some particular cases. The above equation is true when at least one of the following sets is finite. Why though? What is the reason for that? And the reasons are these. By proposition 7.1.11 part E and proposition, another one is there, 7 to 14 part C. Okay, let's see what that means. If both of these sets are finite, then can you say something about this set, the set of those values in X or those points in X at which F does not vanish? One thing you see immediately is that we have this relation. Union why is this relation there? It just simply comes from this. Instead of considering the entire x1 and the entire x2, we are considering only those points where F does not vanish. So that is the restriction we are applying throughout this relation, and we get this relation. Or if you still want to see it more clearly, just take one element here. Then that element, of course, is in X, for which F value is non-zero. But being in X, that element is either in X1 or in X2. So, and of course, the F value at that element is non-zero. So that means that element is either here or here. So that means that element belongs to this union. So that way this is a subset of this union, and conversely also this is a subset of this union, which is in fact easier to show because both these sets are, as you can clearly see, they are subsets of this set, so their union is also a subset of this set. So that's how you get this thing. Now what we are saying is that if at least one of these two sets is finite, then this relation or this equation is true because of these results that we saw previously. So what are the possibilities? Both of them can be finite. Okay. In that case, automatically this is also finite because then it's the union of two finite sets. And keep one more thing in mind, that just like their union is this set, their intersection is still empty. X2 still empty. That's because originally there is no point that is both in X1 as well as X2. X1 and X2 are disjoint, so these are also disjoint. So that means here we are, if this is the case, that this is finite, so this is also finite. So that means what identity here we are looking at, that involves sums over finite sets. And when you have a situation like this, that is you have two sets, this one and this one, and they are disjoint, then the sum of such sums is another such sum where the variable varies over the union of these two sets. That means this. And that is proposition 7111E. And a similar one, there is of course another case where exactly one of these two sets is finite and the other one is infinite. But that infinite is a special kind of infinite. It's not just any infinite set. Say this is finite and this is infinite. Then of course at least one of them is finite. But we already know that this set is at most countable. So it is infinite means it is countable. Okay. And in that case, what can you say about this set? This is finite, this is countable. So their union is going to give you a countable set. So that means in that case, since this is countable, so this sum turns into an ordinary infinite series. This sum also turns into an ordinary infinite series, and this is the finite sum. And such an identity we have already proved in propositions 7 to 14c. So that's how, if at least one of these two sets is finite, then we already have our identity. This is not a part of the solution, it's just for our own sake. So I put them between horizontal bars. Okay, so now we are left with the case where none of them is finite, both of them are infinite, and so both of them are countable as well, because we already know due to absolute convergence that whenever they are at most countable. So whenever they are not finite, they are going to be countable. So assume that none of the above sets then both of the, there is no need to put it in the same line, then both of them are countable. Okay, now after this things get a bit messy. So let me carefully write what we have next. So next what I do is this. Since they are countable, so they will have bijections with the set of natural numbers, because that's what countability means. But we are not exactly going to take bijections with n itself, but we consider a bijection of the first set with the set of even natural numbers, and the second set with the set of odd natural numbers. That is also possible, and here I write things in a somewhat compressed manner, not writing everything. Let me write and then I will explain. It is not difficult to set of bijections alpha from the set to, I will define what 2n is, 2n onto the first set and another one beta from the complement of 2n in n onto the second set. It is not difficult, but how is it not difficult? That is because these, just like, okay, what would you have done if you had n here, only n? You already know that by definition there exists a bijection between n and this, right? So you can use that bijection, any such bijection, to write a bijection which goes from 2n to this. And where, of course, let me complete it, 2n is the set of all even natural numbers. This is not a notation that I have made up, which you can already find it in algebra. Okay, such things are there. Now let's come to the question of how one can be sure that such bijections exist. The thing is like, let me show it here. No? What we have here is that this is already countable, so its elements can already be arranged in a sequence using natural number labels. That is, you have an element which is labeled by 0, then an element which is labeled by 1, then an element which is labeled by 2. If you go on like this and continue your sequence, then you take into account every element of this set precisely once. That's what having a bijection with the set of natural numbers means. So already there is a sequence, so we can write this set itself like this, say A0, A1, A2 and so on. This is this set. On the other hand, you have the set of even natural numbers, which are of course excuse me, 0, 2, 4, 6. So you can write 0 is of course 2 times 0, 2 is 2 times 1, 4 is 2 times 2, 6 is 2 times 3 and so on. So what you can do in order to set up this alpha, you map 0 onto A0, 2 times 1 onto A1, 2 times 2 onto A2 and so on. So this, let me write one more. So that's how you can set up a bijection. Since this is so natural and so obvious, I have not bothered to again write about that also. Similarly, this is also countable. So its elements also can be arranged in a sequence, and the odd natural numbers here you have, they are of course 1, 3, 5, 7, etc. So you can map 1 onto B0, 3 onto B1, 5 onto B2, 7 onto B3. So if you are wondering how one gets these subscript suffix values, it's just this. If you have, say, n here, then it is B n minus 1 divided by 2. Let me see if that is true. 1 goes to 1 minus 1 by 2, that is 0. 3 minus 1 divided by 2 is 1. 5 minus 1 by 2 is 4 over 2 is 2. 7 minus 1 over 2 means 6 over 2 is 3. And so that way it goes. The fact that these sets are countable allows us to first of all have such sequences and call that sequence, or rather its elements themselves, as these sets. So then we can set up these functions alpha and beta, and you can prove, if you are really going rigorously about everything, absolutely everything, you will then need to prove that alpha and beta are bijections. So they can be proved in a very easy manner. If you want to go with that much trouble, then you will do that, or you can just see that this is something which is true. Okay, so anyway, I am just writing only this much. So we now know that such bijections alpha and beta exist. So the function gamma from the set of natural numbers into this set defined as, or defined by this formula, gamma of n equal to alpha of n if n is even and beta of n if n is odd, is itself a bijection. Okay, so now using alpha and beta, we have defined a third function. This, however, has the set of natural numbers itself as its domain, and the range is this, which we know is the union of these two sets. And showing that gamma, first of all, is a well-defined function, and that it is both injective as well as surjective, that is one-to-one and onto, that I leave to you. And in showing these things, you have to use that alpha and beta themselves are well-defined functions and they are bijections, so that is why gamma is a bijection. These are some routine tasks, so I leave that to you. And now we come to the more important part. Again, it is not difficult, so again another such thing is coming. Do not lose patience, but you have to have the level of understanding in order to be able to do these things on your own. Now or sometime later, but you have to get this. It is not difficult to show the following. this is going to be a little big, so I need space. And this is a small hint, use induction. So I am now going to write an identity involving the f values. Should I first write that n belongs to f? That is understood. Okay, so let me just write the formula itself. Summation of f of gamma of I as I varies from 0 to n is, it's a two-part formula, is equal to summation f of alpha of j as j varies from 0 to n over 2 plus summation, have I written it correctly? I think it will be 2j, because we are considering that kind of, yeah, it has to be 2j, otherwise it does not make sense. Let me first write the thing down and then I will then we will discuss. Here in this next one, f of beta of 2j plus 1, where j varies from n to n minus 2 over 2, provided there is a condition if n is even. Then we have this, whereas if n is odd, then in the first sum j varies from n minus 0 to n minus 1 over 2, and in the second sum also the same variation, but here it is the beta values. If n is odd, okay, so this is, where should I put the equality sign? Somewhere in the middle, and this is your formula. Now what do we see here? Let's first try to figure that one out. What is this? This of course is just a sum involving finitely many f values. Now before we see what this formula is about, let us also recall alpha and beta, because we do not have it here, no? Alpha originally is a bijection that is like this. And beta is this bijection. They are bijections. And gamma of course has been defined in terms of alpha and beta both. Okay, so what do we see here? We see here f values, and here we have claimed, and I assume that say we know this, we have proved that gamma is a bijection. So when you consider the gamma values, what are the things that you get? I mean, what are the gamma values? The gamma values, of course, are the elements in this set okay, because that's what they are, and their f values we are talking about. So we are talking about a finite sum having finitely many such f values where I varies from 0 to n. On the other hand, if our n, that n is even, then what we are claiming here is that this is equal to this sum plus this sum. Now you can see one thing, that alpha is a function whose input is an even natural number. So that's why we have 2j here, because otherwise it would not make sense. So that's why I said there that it has to be 2j, otherwise it does not make sense. Just like that, the input of beta is an odd natural number, so we have 2j plus 1. And the variations, of course, there is nothing to say unless we go for proving it, or we see some cases in which these formulas are true. Now the proof, of course, I leave to you. Okay, you can apply your standard induction on n, of course, and you will see that you can prove this in this form itself. But be careful, because the induction will not be a straightforward one. That's because our claim itself depends on the parity of n, whether it is even or odd. Depending on that, the claim changes form. Now, let us, so what can we do now? In order to at least see that this is plausible, we cannot immediately claim, I cannot claim now that this is true. I am just simply saying that this is true, but let us at least take some values of n and actually see whether we really get these things. So this is for our understanding. So let me put a bar here. Let us first take the smallest possible values of n. When n is even, the smallest possible value is 0. When n is 0, what is this sum? There is just one term in this sum, which is f of gamma of 0. And that should be equal to, if this formula is true, that should be equal to this plus this when n is 0. Let's see. When you put n equal to 0 here, actually what do you get? Minus 2 over 2, that means minus 1. It looks very strange, but it's not illogical or ill-defined. You can have a thing like this, a sum like this. Now if you go back to the definition of such finite sums, you will see that in that definition, we do not really necessarily have to go from a lower number to a higher number. The opposite also can happen, but in those cases, the sum is defined to have 0 value. It's not meaningless, but its value is 0. And here, of course, you have only one sum, only one term in this sum, and that is f of alpha of 0. plus 0 coming from here. So this is f of alpha of 0. But we have f of gamma of 0. But you go back to the definition of gamma. Gamma of n is defined to be equal to alpha of n when n is even and 0 is even. So alpha of 0 is actually gamma of 0. So in this case, yes, our claim is true. Let's take another value, say n equal to 1. There is no point keeping it because I want to keep that formula. So let's erase this part and let us now take n equal to 1. So if we take n equal to 1 here, then unlike the previous case, here we have two terms, f of gamma of 0 plus f of gamma of 1. Now that we have already seen a little about these things, so we apply the definition of gamma. Because 0 is even, so gamma of 0 is actually alpha of 0 and 1 is odd, so beta 1. Now according to this claim, this part of the formula should be true. So let's see what we get here. In this part, if n is 1, then this is 0, this is also 0. F of beta of 2j plus 1, where j varies from 0 to 0. That means in each sum we have one term only. So you will have one term here and one term here. So that you will get just simply by putting j equal to 0. So if you put j equal to 0, this one gives you f of alpha of 0. And if you put j equal to 0 here, then you get f of beta of 1. See? Same. Now let us take a somewhat large value of n. Large in the sense that not this small. Okay, so n equal to 0, n equal to 1. In these cases, the formula has been true. So already you have basis for your induction. For the base case, you need not consider n equal to 1, of course. You can start with n equal to 0. Okay, what can we take? Say n equal to 5, say. So if n is 5, then this becomes what? For this, we of course need not think about anything, we just simply write the sum. F of gamma of 0 plus f of gamma of 1 plus 2 plus 3 plus 4 plus 5. And now we apply the definition of gamma once again. So this becomes f of alpha of 0 plus f of beta of 1 plus f of alpha of 2 plus f of beta of 3 plus f of alpha of 4 plus f of beta of 5. Okay, because n here is odd 5, so let's calculate this. 5 minus 1 is 4, 4 over 2 is 2. So the first sum is this. And the second sum is again 2, okay. So from this one, what shall we get? F of alpha of 0 for j equal to 0. For j equal to 1, f of alpha of 2, and for j equal to 2, f of alpha of 4. And from this one plus for j equal to 0, f of beta of 1. For j equal to 1, 2 times 1 plus 1 is 3, f of beta of 3, and for j equal to 2, 2 times 2 plus 1 is 5, beta of 5. Let's now see alpha of 0 to 4. 0 to 4. Beta of 1, beta of 3, beta of 5. And that's it. So this way it seems plausible. I know that it is true, but for you it seems plausible that the formula is true. So you just have to prove it by induction. Okay, so now that we have this formula, you may be thinking suddenly, what is it that we have started? Alpha, beta, gamma, and this somewhat intimidating looking formula. They are essential. It will become clear soon why. And now next what we have, now we use the fact that these sets, the set of even natural numbers and the set of odd natural numbers themselves are countable. Now define alpha prime from n into 2n by alpha prime of n equal to 2n and beta prime from n into the set of all odd natural numbers by beta prime of n equal to 2n plus 1. Now with the help of these new functions, these are of course clearly bijections. Again, clearly means you have to show it or at least convince yourself that they are. Clearly alpha prime comma beta prime, these are bijections. Hence the following functions are also bijections. One of them is alpha composition alpha prime. So alpha originally is a function from 2n to that first set which has x1, and alpha prime maps n into n onto 2n. So alpha composition alpha prime maps n onto this. This one, and beta composition beta prime maps, beta prime maps n to n minus 2n or n difference to n, and beta then maps that to the second set. And because alpha, beta, alpha prime, beta prime, these are all bijections, so the compositions are also bijections. we have had to go through this much trouble just in order to turn the sums, the three sums, into ordinary infinite series, because to do that we need a bijection, and that too a bijection between the underlying set over which your variable is varying and n. Okay. Now you remember what type of function was gamma, original gamma. Gamma was a function from n into this, and we claimed back there that gamma is a bijection, which you have to show. Now this is a bijection between n and this set. This is a bijection between n and this set. This one is between n and this set. So using these bijections, we can turn the three sums into infinite series. We can of course take any bijections, but that will not allow us to show our identity. So that's why we had to go through all of these things. Okay, now we use this fact and these new functions alpha prime and beta prime to write something now about these formulas. Okay, I hope we have already properly seen whatever we have to see in this part. So just to keep that thing intact for now, I will have to erase this. So that means here, let's just see once more. We next considered these functions, which are themselves bijections. So using them and the original alpha and beta, we created this kind of bijections. Or let me just keep this lower part and next write from here. So for any natural number m, we have this summation f of gamma of I, where I varies from 0 to 2m, and we use this formula. Okay, so we just straight away use this. Because the n here is 2m, it is even, so this part of the formula is used. So what do you get? Just simply if you put n equal to 2m, in place of n if you have 2m, then n over 2 becomes first of all m. So you get f of, but let me write this afterwards. First of all you have m here and j varies from 0 to m. But now instead of writing 2j, I am going to write alpha prime of j, because that's what the function alpha prime is. It maps every natural number onto twice its value. J gets mapped onto 2j by alpha prime. So 2j just simply means alpha prime of j, and alpha of alpha prime of j means, do I have space here, alpha composition alpha prime of j. So this is just this plus the same thing we are going to do here. So if I again in place of n if you put 2m, then 2m minus 2 over 2 is m minus 1. And 2j plus 1 is beta prime of j. Compose that with beta, you get this. And another one where in place of 2m, I think we have 2m plus 1. Yes. Yeah, now I have to get rid of this. Again, j varies from 0, but this time to 2m plus 1 f of gamma. Oh, I wrote I here, no, on this side. So let me maintain that I equal to 0. Actually, it does not matter what name you give to this variable. It's a dummy variable, but still, let's make it uniform. Okay, so now 2m plus 1 is odd, so we use this part of the formula. If you have 2m plus 1 here, so that plus 1 minus 1 cancel out, 2 cancel out, so you are left with m. And again, using that trick, here you have alpha of alpha prime of j, where j varies from 0 to m, plus here also we have the same thing, so we will have m here, f of beta composition beta prime of j. So do you see that we have, using these bijections, very cleverly written a partial sum. I mean, how can I express this? We have seen this formula enough, so now I erase this part. See, this is the thing. On one hand, we have this sum. No. We know that this set is countable. So if you have a bijection between this set and n, then you can turn this into an ordinary infinite series. That bijection is gamma for us. So that means, by definition, this becomes this infinite series. Okay. And similarly, you have the other two sums. What bijection do we use here for this set? Between n and this set, we already have one, that is alpha composition alpha prime. So using that bijection, this turns into this series. And using that other bijection between n and that other set, the third one is turned into an ordinary infinite series. x2 j varies from 0 to infinity, f of beta composition beta prime of j. What we are trying to show is that the sum of this series is equal to the sum of this series plus the sum of this series. Now we know what their sums are. They are limits of their respective sequences of partial sums. The sequence of partial sums of this series looks like this. Partial finite sums. The one for this series looks like this. You can take 0 to n, say, because n is after all n, where n itself varies from 0 to infinity. And the one for this series is similarly this. So that means we are trying to show that the limit of this as n approaches infinity is equal to the limit of this plus the limit of this. And these individual terms of these sequences are related to one another by these formulas. You can see that. So, now that we know that they are related like this, where you can see that the terms, that is these forms f of gamma phi, f of alpha, whatever we have, they are not changing in these sums. Only the limits are changing. Limits means to what integer the sum goes, that thing is only changing. So now what can you say from these two equations? From these two equations, you cannot of course immediately say that the limit of this sequence is equal to the limit of this sequence plus this sequence, but rather these two formulas give you subsequences of this sequence, one in which we have only even limits, that kind of sum, that is for even n. That subsequence has these terms, and that is equal to this plus this. So that subsequence has what kind of limit? That will be the limit of this as m approaches infinity. That is equal to the limit of this as m approaches infinity plus the limit of this as m approaches infinity. But that is, these are just simply this, the limit of this is the limit of this ordinary sequence, and the limit of this is the limit of this ordinary sequence. Note one thing, that as m approaches infinity, it does not really matter whether we have m minus 1 or m here. This still approaches to the limit of this sequence. Okay. Similarly, if you consider the other subsequence of this where n is odd, then you get this kind of sums. Here also, if you take limit as m approaches infinity, that is the limit of this as m tends to infinity plus the limit of this as m tends to infinity. Again, the limit of this plus the limit of this. So, both the subsequences of this sequence, one where the n's are even and the one where the n's are odd, they converge to the same limit, and that is just the limit of this plus the limit of this. In other words, this series value plus this series value. So now we are going to write that. Hence, both the sequences I equal to 0 to 2m f of gamma phi as m varies from 0 to infinity, and the other one is the one where the sums are these. Here also m varies from 0 to infinity. Both of these sequences, which are subsequences of the original, we have already seen that. converge to let me write it directly instead of writing all those things, limit of that and that. Ultimately, this plus this. But we have already seen something we saw a while back, quite a while back, when we were studying sequences, that when you have a sequence of real numbers for which these two subsequences this and this both the subsequences are convergent and they have the same limit. If we have that, say this also converges to L and this also converges to L as n approaches infinity, then the original sequence is also convergent and converges to the same limit L. We are now going to use that here. So that means, and we will of course have to refer to that place. I mean, we have to mention where we are getting that from. It then follows from the solution to exercise 664. I wish it was 666. That let me write it directly. Okay, so what you know what I'm trying to say, that the sequence, this sequence where in place of 2m we just simply have n, that also converts, the entire sequence converges to this plus this, that is this plus this, the other sum. And that's how we complete the proof of that identity. But we are not done yet. Keep in mind, we have only proved a part of subdivision C. There is another part, and that part, let's now recall that part. That part is this. You still have x, we still have our set x, but now we are not considering functions f or t. We have another function h, also a real valued function defined on x, for which of course we can consider this sum. Now we do have x1 and x2 like before, that is x is their union and they are disjoint. But what is given now is this. This and this are absolutely convergent. That is given. Then we have to prove that this is absolutely convergent and the sum of this is equal to the sum of this plus the sum of this. The showing that this is equal to this plus this is just that previous thing only, because once you have that all three are convergent, then we have just now proved it. So now our aim is to just show that this is also absolutely convergent. It's given that this and this are. Okay. So we do that in this next paragraph. Okay, so what do we need to prove that this is absolutely convergent? Go back to the original definition. For any finite subset A of x, we have, say we start with this sum. H, we are no longer having the function f. Okay. From these relations, what can you say? You can say two things. One is that A is the union of these two sets. How do you get this from here? You just take the intersection of A on both sides. A intersection x is of course A, because A is a subset of x. And if you take the intersection of A with this, then you use distributive law that gives you this union and intersection. They distribute over each other in both the ways. And also at the same time, if you take intersection here, then you get this fact as well. Okay, so that means we can write this sum like this. Now note that here we are dealing with finite sums, and you have a finite sum in which the set over which you are considering the sum is a union of two disjoint sets. So from a previous property of finite sums, that is just equal to the sum of these two sums plus and you can write the reason here why that is true. That is precisely which result we are using here in this step. Do I have it here again? Now, unfortunately, I have not written it here, but you can understand. What you have to do is you have to go back to the properties of finite sums like this. There you will see a property which will allow you to write this. In writing this, you have to keep in mind that these two sets have to be disjoint, which we have seen they are. Okay. Now, excuse me, something went in my eye. Now, note carefully that this is actually a subset of x1. It's a subset of x1 because it's of course a subset of x1. It's the intersection of x1 with another set. At the same time, this is finite because A is finite, and this is just like it's a subset of x1, it's a subset of A as well. So this is a finite subset of x1, and it's given that that sum is, which has x1 here, that is absolutely convergent. So this thing is less than or equal to t1, and this one, this is a finite subset of x2, is less than or equal to t2, and that is less than infinity, where A is finite and T2 is the supremum of the other set. Again, A is finite. Of course, you understand that the A here is not a fixed set, it is being used as a variable. Okay, it's nothing fixed. And because those two series are given to be absolutely convergent, so these two suprema, T1 and T2, are themselves finite real numbers. And this now becomes less than or equal to T1 plus T2, so which is also finite, it's less than, strictly less than plus infinity. Hence, and this tells us what? This tells us that this kind of sums are all bounded from above by a finite number, by a real number. Hence, the supremum of this set itself is less than or equal to T1 plus T2, which is less than infinity. Hence, x, you can write x, but in the text it's written x1 union x2 is absolutely convergent. Now, by what we have already proved above, it follows that we also have this formula. Now part C is over, and there is part D also. I won't solve part D fully, I will leave a part of it for you. So let's recall first part D, its statement. In part D, we again go back to the original sum, that is sum of f of x, where x varies over the set capital X, that is given to be absolutely convergent. And now there is another set y, and say we have a function phi from y into x, which is a bijection. Then we have to prove that this sum is absolutely convergent and its value is equal to the sum of the value of the original sum. That is part D. I will not prove this identity. This identity will be left to you to prove. See, you try and see if you can get it. If you do not get it, or you have some kind of confusion about how to proceed, then please let me know. What I will do though is that I will prove that this is absolutely convergent. So let's go for that. For any finite subset, it's almost like this one, the previous one. For any finite subset A of y, we have to consider such a subset of y because here the set over which you are considering the sum is y. So we are going to consider this. But this is nothing but summation absolute value of f of x as x varies over phi of a. How we are having this in place of this, that you will get from one of the properties of finite sums. And here luckily, however, I can refer to it because I have written the number. This, and it is given that this is absolutely convergent and phi of a is a finite subset of x. So this will be less than plus infinity. Well, I should not say that this is less than plus infinity, but rather this is less than or equal to the, so let me write that itself, because if I just simply write this is less than plus infinity, that doesn't say anything. Oh, this a and that a can create a lot of confusion. So let me use something else here, say b. Okay, that is just what supremum is, the least upper bound, and it is given that this is less than infinity. Yes. Hence, oh, okay, we need to write the reason for that step before we end this. Note that phi, if you consider the function phi from a to phi of a, then this is a bijection, and so phi of a is a finite subset of x, and use propositions 7(1), 11c here to have this. So the supremum of this kind of sums for this kind of sums, this supremum is an upper bound, so their own supremum will be less than or equal to this upper bound. And this is known to be finite, so that is also finite. Thus, this is absolutely convergent, and this actually does not complete it fully, provided it will be completed provided you show that the sum of this is equal to the sum of that thing, that other series. And when you do that, this exercise is finally over. And I end this video here itself. It has been a long one, no? But that's the way these things are, and things are going to get even longer when we reach the last part, the last section of this 8th chapter, which treats ordered sets. Some quite involved things are there. But anyway, that's just it for tonight, and in the next analysis video we are going to see what comes next. And the next upload is of course this coming Tuesday, and on Tuesday we have, what can we do? Let's go back to vector spaces. We have started inner product spaces, so we will see more about that. So see you on Tuesday with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.